Talk with Ben about building carbon or carbon analysis within Passive House. Ben has been, how long have you been part of EMU now?
About 5 years.
So Ben is what, the New York chapter of EMU, or the EMU office of, or the New York office of EMU, and is if you do one of the trainings with them, you might find Ben as one of the instructors, and he's been a great supporter of Passive House and building science in general. Um, and without any further ado, I'm going to stop sharing and let Ben take over and present.
We do the Passive House tradespeople training all around the country. We also consult on numerous projects throughout the nation, all focused on Passive House or high performance. And today I'm happy to talk to you about a specific part of Passive House that we don't talk about a lot because it's actually not in the standard, but it's something that's very important to consider, which is the total carbon use. So the carbon that's emitted from our building materials as well. So what I'm about to present to everyone is actually some research that has built upon some of my grad students. They did their thesis project analyzing some of the EMU projects that we've consulted on around the country. And I took it a step further to build out a complete analysis to try to compare overall carbon emissions from different projects around the country. And just to note before I jump in, we decided that we would make this conversational. So if you want to hop on and ask a question about a slide, you can throw your question in the chat or you can jump on the mic. I'm happy to just field questions as they come. So keep them coming if you've got things that are burning. So to start off, you're all in a Passive House webinar here, so you're probably familiar with carbon emissions, but I just want to set the groundwork of what we're going to actually be talking about. So carbon emissions is the release of carbon dioxide and other greenhouse gases into the atmosphere. This happens primarily from the burning of fossil fuel. And if you don't know, these gases can trap heat in the atmosphere, and this what leads to the global warming and more extreme weather. Generally speaking, our energy use is directly related to these emissions. And since we're in the building sector, our built environment consumes a large portion of energy. About 30 to 40% of all global energy use goes directly towards the built environment. And unfortunately, most of our energy is still produced by fossil fuels. So the more energy you consume, the more emissions are going to be emitted. So let's look a little bit at the history of emissions and how it's related to energy use. So here we're looking at global primary energy use by source since the 1800s. So you can see from the Industrial Revolution, really when we started extracting fossil fuel, coal, our energy use kind of skyrocketed. And you can see that it's only gone up in this hockey stick, right? So we're only been increasing more and more in terms of consuming this energy. And you can see from the breakdown, our energy consumption is still heavily reliant on fossil fuels. So what does this mean? This means that our emissions are almost directly correlated to energy use. So here we're looking at the CO2 emissions annually worldwide, and you can see that that curve kind of traces right over our energy use line as well. And you can see that this graph has just gone up and up until 2020. The pandemic put a little bit of pause on our emissions. And unfortunately, we are right back going up and up. So we've got to try to combat these emissions overall if we want to stay within our global warming targets for the entire world. And if you don't know those targets, it's generally accepted that a 2 degree Celsius average temperature over the global anomaly temperature is what's considered to be sustainable. If we go over that, there's going to be a bunch of funky things that happens in our climate. So you can see that our global temperature also follows that emissions line, right? So it's the same kind of trend where it's relatively low and then starts to spike as soon as we start to consume more and more energy. And This graph is making me a little bit sad because when I started looking at these numbers back in the aughts, we were really trying to stay below 1.5 degrees Celsius. And I think that's kind of foregone at this point. And so now our goal is really that 2 degrees Celsius. So this is what we're trying to look at. And to put it in perspective culturally, who are the people who have been consuming this much energy and have been producing the emissions? So what we're looking at in this graph is by region around the globe, who is accounting for most of these emissions. And guess what? USA, number one, right? So we are well beyond other parts of the world in terms of our energy consumption, and therefore we're up and away with our CO2 emissions. So whether you're here in the States or abroad, I feel like a lot of our kind of more developed areas in the world, we bear a brunt of this responsibility to see if we can make a dent in this trend and see if we can reduce our emissions. So that got me down the path of looking at Passive House, because if you don't know about Passive House does a really great job of reducing energy consumption. And it specifically looks at something called operational carbon. Operational carbon emissions are the emissions associated with operational energy use. So our buildings consume a lot of energy. We consume energy for heating, cooling, ventilation, lighting, heating hot water, plug loads, appliances, all that consumes energy. And the more energy we consume, the more emissions that we emit. The goal is to try to make our energy have less a reflection of CO2. So we want to use fossil fuel energy inputs. But unfortunately, as we saw before, most of our energy sources are still derived from these fossil fuels. So even if you're pulling electricity for your building, that electricity might be powered by a gas power plant or a coal power plant, in which case the burning of that fossil fuel has a lot of emissions associated with it. Operational carbon emissions is something really important to think about, because this is something that gets consumed once the building starts its operation, and it's going to continually get consumed year after year. And we measure this energy in either kilowatt hours per year or kBTUs per year. And again, these amounts of energy, they're pretty much directly correlated to our CO2 equivalency, so the emissions that are associated with that. Operational carbon does not include any of the energy related to the construction of the building, the materials used in that building, how they're produced, or how they're transported. So Passive House is really good at looking at this one specific part of our energy use, and we can really reduce our operational energy if we go towards this standard. However, the standard does not talk about embodied carbon. Embodied carbon or embodied energy, these are the emissions associated with the extraction, manufacturing, transportation, installation, maintenance, and disposal of the building materials. We look at something called a life cycle analysis, an LCA, defined by the ISO standard 14040. Essentially, what we're looking at is we're looking at the entire lifespan of a given product. And that starts from the product stage, the cradle to gate. This is where the material is extracted. It is then transported to a manufacturing facility. It's fabricated into an actual product. And then we enter the construction stage. And that's where we transport that material to the site. And then we install that material in our building. And that is that part of the stage, the construction stage. Once everything is constructed, we then enter the use stage. And this has a lot to do with the operational carbon, but it also could be, maintenance required on those materials, or any upgrades or any replacement. That all goes into the use stage. And finally, there's the end of life stage. And this is, the deconstructing and disposal of any of these materials. So what's the waste stream? It has to get transported. Is it going to landfill? Is it going back into the production cycle? These are all questions for specific products. So you can do this entire life cycle analysis, and there's tons of research out there about different materials and how how much emissions are associated along the entire chain. For this analysis, we're going to focus in on the product stage, so cradle to gate. And the reason we're doing this is this stage really accounts for the most amount of emissions along the entire chain. Anywhere from 65 to 85% of the total emissions of a product's life cycle comes at this production stage, A1 through A3. So we're going to kind of focus in here throughout this analysis. So when we're thinking about material choices in our buildings, I like to group them into three main categories. We have materials that you're either drilling for, so these are petrochemical-based materials. You have materials that are being mined, or you have materials that are being grown. All of these materials are going to go through a manufacturing process. And they're going to start with a raw material, and then we're going to synthesize them into some finished product. And depending on what the source material is and the manufacturing process, we're going to have more or less total emissions associated with developing these products. So if you're thinking about a material that you're using, you can quickly put it into a category. Hey, did we have to mine for this material? Did we have to drill for it? Or was this grown or produced biogenically? So we're going to dive into some of these materials in a little bit more detail here. So let's start with the petrochemical based or the drilled materials. There's many products that fall under this category. I'm just showing two of them here just to kind of get you a taste of what the analysis is actually looking at and what we're studying. So first we're looking at spray foam. This is a two-part chemical mixture. When we combine them, you get this exothermic chemical reaction. And in that reaction, we're adding some additional material, including a blowing agent. And these are usually HFCs, hydrofluorocarbons, and these blowing agents add pockets within the foam, and those air pockets or those gas pockets are what gives the material its insulated quality. So you get this expanded rigid foam here. You can kind of see this coming out of the popcorn. You mix the two agents and it expanded. We usually do this process on an actual construction site. So this is the on-site spray foam that you see being applied here. The two things are mixed together. You blow it into your cavity, into your roof assembly, and it'll expand and create this rigid foam. In terms of embodied carbon and embodied emissions, this product is really high. It's on the higher scale because not only did we have to originally drill for it, but we added additional chemicals and energy along the way. So to produce these chemicals and to add the blowing agent, that also has a pretty high global warming potential. So there's more emissions associated with this type of product. A slightly less emitting product, but still higher on our scale, will be something like polystyrene. This is either in XPS or EPS form. Here we're looking at the EPS process, so the expanded polystyrene. Here we're looking at the raw product, which are these little polystyrene beads. Polystyrene is just a polymer that's just manufactured by petrochemicals, so through oil. These polystyrene beads get heated with steam and they expand in size. At the same time, we also add an additional blowing agent to trap still pockets of air within the material. That material then dries out and gets stable. And then we add another heated process in a mold where we shape the actual beads. They fuse together and they get molded into a big block. That block is then cut into final dimensions and we get our final EPS board here. And again, this has fairly high total emissions. So we're looking at kilogram carbon CO2 emission equivalent. That's what the kg CO2e is. So these are both petrochemical, both a little bit high on their total emissions. If we shift gears and we look at a mined material, we have two examples of mined materials here. We have fiberglass and mineral wool. The fiberglass process actually uses a fair amount of recycled content to begin with. So we have a combination of sand, recycled glass, limestone, and soda ash. These are the raw materials that go into making the fiberglass insulation. We heat up these materials really hot, 2,500 degrees Fahrenheit. We create this molten glass. The molten glass gets sprayed through a nozzle through this fiberization process. The nozzle creates these really thin glass strands, kind of think like cotton candy, right? They're kind of being whipped around. Those strands then get laid on a conveyor belt. There's a binding agent that's added to it, and we actually form these little bats. And these bats then get heated and cured so that the binding process is finalized. And then you get that pink bat that's very familiar if you've ever seen any insulation before. This is probably the most common type of cavity insulation we have.
Hey, hey
Because,
Ben, let
yep,
me jump in here for a quick question here. Charlie was asking if you could explain the range in total emissions, 46 to 557 kg COE.
sure. So these emissions, so what I'm talking about is like a default material, fiberglass, XPS, EPS, but there are a bunch of different products that have different specifications. They might be different densities, they might have different R values, they might be from different manufacturers. So these numbers are specific to, your total emissions are specific to a specific manufacturing process. So it really does vary depending on what product you use. So these are general figures. So kind of the low end to the high end of where these products can fit in. So hopefully that answers it a little bit. And it's a good question. So you can see that the range here for fiberglass is 15 to 42. So a lot lower than what we were looking at in the slide before. And I should have mentioned that this is for the equivalent here is looking at when we're installing this material. It's 100 square feet of this material to get an R value of 20. So that's the baseline for all of these insulation materials. And I think that note was on the previous slide. So just to reiterate that it's 100 square feet of material with an R value of 20. So we can kind of normalize all the materials. So we're looking at the same baseline. If you want to insulate 100 square feet of your wall to get an R value of 20, which is roughly around what a code minimum R value is for many places in the country. So with that being said, fiberglass has a way lower overall emissions than the foam products because of the recycled content, right? We're still adding a lot of energy. If you think about heating glass to this temperature, we need to input a lot of energy there. So a lot of that energy gets compensated for by having a high recycled content. So this is a big reason why this is a slightly lower embodied carbon material. Then we look at something like mineral wool, which also has some recycled content. It's made out of rock and recycled slag from steel manufacturing. The rock essentially gets melted down, similar as the fiberglass. It gets melted down, and there's another fiberization process where the heated rock, which is essentially lava, gets strung into these strands, and you create this wool, this mineral wool bat. And these strands get woven together. There's a binding agent, which is typically formaldehyde or traditionally formaldehyde. And then they're layering this bat over itself, compressing it, and curing it again in an oven. So adding more heat. And then you're cutting it to size and you get this finished product, which could be a board, a bat product, or there is a loose fill version of this as well. And because we're melting rock, there's a good amount of embodied energy that can be in this product. If the product doesn't have a high recycled content, then this becomes a lot higher. If it's more recycled content, it's on the lower scale. And what I've heard anecdotally is that there's been such a demand in this product that the waste streams, the recycled waste streams, are not quite keeping up with demand. So they have to use a lot more raw material, a lot more raw rock, and that leads to a higher embodied carbon. And then our final category, grown or biogenic. These are materials that are pretty much sourced from nature. So they're either grown as a plant or as an animal. In this case, we're looking at wood fiber insulation and cellulose insulation. Wood fiber is mostly made out of raw wood. The raw wood is chipped together, milled, and dried. It's then sent into a process where there's a binding agent added This could be a natural lignin or a polyurethane binding. Some of it gets paraffin that's added for waterproofing. That material is then compressed and heated to create these bonds between the fibers. And the final product can be a wood fiber board or bat, or they also have loose fill product. And because we're using a grown material, the embodied carbon of this type of material is very low. In fact, it's considered negative. And what do we mean by negative? Well, if you think about the manufacturing process of wood, how are we manufacturing this product? We're not strip mining, we're not drilling, we're actually growing these trees. So throughout the product's manufacturing lifespan, it's actually pulling carbon dioxide from the air and getting stored in the material. So we're actually taking carbon out of the atmosphere, sinking it into our building material, and then locking it into the building for the lifespan of the building. So that's why you see these negative numbers, because it actually accounts for taking carbon out of the atmosphere. So more carbon is removed than is input in the energy process. So this is a good thing when you see a negative value here. Another product that has this characteristic is cellulose. This is recycled newspaper. Very, very high recycled content because it is recycled newspaper, just like the image shows. This newspaper just gets shredded to pretty fine particles. It gets monitored for moisture content that might need to be dried out. It goes through a sorting process where any miscellaneous metal that was in the mixture, a big magnet comes and pulls that metal out. The shredded paper then goes into a vat where there's some boric acid that gets added. This could be a boric acid or borate salt that's used for fireproofing. So there is a fireproofing added to this material, and it comes in this loose fill product. And this can be a loose fill or a dense pack in your wall assembly. Because it's made out of paper and it's recycled content, again, it's got a very low embodied carbon emission. So just to look at standard kind of building insulation materials, here we're looking at the equivalent of 1 square foot of this material to get to an R40 wall. Now, an R40 wall is typical when we're starting to talk about passive house levels of performance. So you can see the thickness of material of what you need to get to that R value here below. And then you see the kilogram CO2 equivalent per square foot here. So our larger embodied carbon materials are the petrochemical based, closed cell, XPS, polyiso, EPS. Then you can see that our mineral products are kind of in the middle. They have a large recycled content, so it reduces that. And then anything that's grown, hemp bat, cellulose dense pack, these have a negative embodied carbon consideration. Next, we're going to look at the embodied carbon between windows. So the reason I'm singling out insulation and windows is this is the real place within our building where added performance means we need to use more of this material. So to get to higher R values, we need to have more insulation. It's just what we need to get to those levels of performance. Same thing with windows. We need to add a third pane in many climates to get to the required performance that we want. So adding more glass has a huge impact on the embodied energy of the material. Glass is energy intensive to make. So here we're kind of showing, a typical window size, 4 by 5. That's the NFRC kind of standard window, so 20 square feet. And the equivalent, depending on whether it's a double pane unit or a triple pane unit, and what type of frame is used in the window. So in this case, our higher side is a 3-pane fiberglass window, and the next is our 2-pane fiberglass. So this is kind of showing that fiberglass has a fairly high embodied carbon. Then we can see that there's a triple pane UPVC, so a plastic frame. And then we see a 2-pane wood with aluminum cladding. The aluminum is highly energy intensive, so this makes that product a little bit higher. Then we have the 2-pane UPVC. Then we have an interesting difference between if the window is made in the US and Canada or if it's made in the European Union. Now, the EU has more strict standards on embodied carbon, and specifically on LCAs. So you need product declarations and LCAs for products that you create. It's a little bit different than here. So their manufacturing processes also have lower embodied carbon at the forefront. So their products are starting with a lower embodied carbon. So you can see that the triple pane wood aluminum clad is lower here than the two pane American version. So we're actually starting off with a little bit less energy if we're looking at Europe, a European product. And you can see that the best product here is actually a European made all wood window. So very little aluminum, all wood is renewable, and then following a European manufacturing process. But if we're thinking about total carbon, there is a penalty from ordering things from Europe, right? So we might have a better performing window. However, there are some transportation emissions associated with bringing that material from Europe here to the United States. And it kind of depends on what mode of transit that we're using, whether it's something that we would want to do or not. It also depends where our project is. Are we on the East Coast or on the West Coast? Because the distance traveled is going to have a huge effect on the emissions of the material. So here you can see that air freight, that's the highest potential carbon emissions. This is kilograms CO2 equivalent per ton of material traveling per mile. So the one thing that is in our favor if we're looking at importing things from Europe is that sea freight is actually a fairly efficient way to move materials. You can think of those containers of having thousands of containers on those ships. So per unit of things that we're moving, it's relatively effective, even if the fuel source for these sea liners are not great. They're pretty bad emitters, but compared to the actual material that we're moving, it's fairly efficient. So it might be worth importing a high performance triple pane window from Europe if we're only bringing it to the Eastern seaboard and we don't need to truck it a big distance. If we do need to move continental distances, the best way we can do this is via rail. So that brings me to the meat of the presentation, which is this case study that I mentioned earlier. This case study is based, again, as I said, on some of my students at City College here in New York City. So it's part of the CUNY system. They started to think about this total carbon use. So looking at the material side, the transportation, and the operational carbon. So in this case study, I kind of built upon their research and did an analysis on 4 real-world projects that we at Emu Passive consulted on. So we're looking at 4 projects across the country, mostly in climate zones 4 and 5. So think of Denver, Colorado, think of Seattle, Washington. In this analysis, we modeled all 4 buildings to 3 different energy standards. We modeled them to code minimum, so 2021 residential code. We modeled them to the Department of Energy's Zero Ready Home standard. And then we modeled them to the Passive House standard. These are the Zero Energy Ready Home and Passive House standard are voluntary standards that anyone can apply to. The residential building code, of course, is mandatory. We use the Passive House planning package, which is the energy modeling software to calculate the operational energy use of each standard. And then additionally, we looked at what if we looked at the materials that make a passive house a passive house. So what are the extra materials that go into making passive house? I kind of alluded to it in the slides before. We're going to need extra insulation and we're going to need better performing windows. So the research question is this extra material needed to achieve the passive house standard worth it in terms of our total carbon emissions? So if we're doing a really, really efficient home, but we spent a ton of energy with the materials that we use to build that home, is that something that we should strive for? So that was the research question. So what we did in terms of analyzing the embodied carbon is we looked at specific sets of materials. I looked at the embodied carbon for insulation, windows, compared to all the standards. So I'm not looking at the embodied carbon of the entire building. we're assuming that the buildings are going to get built. So you're going to be using the same amount of energy to build a code built building to a passive house building. But what would be the extra amount of energy needed to get to that passive house level of performance? So along the way, I used the Beam calculator. This is a free tool, which I highly recommend people check out. This gives you a really easy way to try to account for carbon use in your building. It's got a full database of materials with their calculated embodied carbon values. So it's a really cool tool that I got to explore pretty deeply in this analysis. For the material analysis, not only did I look at the different quantities for the different energy standards, I also looked at different material packages. So I looked at 3 different scenarios, pretty much imagining what if we built a building with conventional materials? What if we used a more high embodied carbon material to get a little bit higher performance? Or what if we used low embodied carbon materials? So just for those following at home alone, the case study variables for modeling, these are the different packages that I used, as well as the energy standards. So essentially, when we're looking at the code minimum building, we're going to need specific R values at the different assemblies. And the Department of Energy also has specific targets for their building. These standards are actually very similar. So the R values needed for code are almost the same for the net zero ready building, but the only difference really is the roof and some basement walls. Where passive house is different is passive house doesn't require a specific R value for its certification. It's a performance-based standard. So you need to meet with a specific amount of energy demand for heating and cooling to comply with the standard. So depending on your project's design, climate, the R values can vary. So I have a varied level of R values depending on what project we looked at and what assembly we're looking at. So these are not fixed values. And then for our material scenarios, my more conventional material package would be using EPS insulation below grade, the fiberglass in our walls and roof, and if we had continuous insulation using mineral wool board. Also looked at a UPVC window, and this is a double pane window. This is the value for complying with code. Pretty much the same value to comply with the DOE, slightly better performance, but still this is a double pane. On the material selection type 2, I was looking at XPS insulation, so a little bit higher performance than the EPS, closed cell spray foam, XPS as continuous, and that UPVC window as well. And I forgot to mention that the passive house window, to get to this level of performance, you need to increase from double pane to triple pane to get this U value. So all the passive house scenarios have triple pane windows. The final low embodied carbon material package is material scenario 3. We have the mineral wool board, dense packed cellulose for the walls and the roof, wood fiberboard for continuous exterior, and then an all wood window. These are the 4 projects. We've got Boulder, Colorado, Kirkland, Washington, Sugarloaf, New York, and Charlotte, North Carolina. The projects are all similar in scale, although there's a smaller one and a larger one. The 2 middle ones are about the same. And what's interesting here is that the form factor, which is the treated floor area of the building over the envelope area, has a big play on the energy use of the building. Not only for operational energy, which I knew from our passive house classes, but also from embodied energy. So just more wall surface you have to insulate, the higher that energy is going to, the higher the associated emissions are going to be. So here we can kind of see the quantity of that total envelope area for the 4 projects. And you can see that the form factor with the highest, so building 3, has a lot more of things that we need to insulate, right? So there's more wall, more roof compared to building 2, even though these are at the same size. This just has a lot more. So keep this graph in mind as we're moving forward, because this plays a big role, the amount of envelope that we have. So if you're an architect out there, you can do a huge job of thinking about energy consumption just by the form and the design of the building, right? So it's something interesting that the analysis brings up. So what we're starting with is we're looking at each building, and we're going to look at the embodied carbon associated with materials in type 1, scenario 1. So this is the EPS, fiberglass, and mineral wool. This is total carbon emissions. So the larger building obviously has the largest energy use. If you're looking at the colors here, the light blue is when we built the building to code. The medium blue is when we're looking at the zero energy ready home, and the dark blue is looking when we build to the passive house standard. In each scenario, the passive house standard had more embodied carbon. Makes sense. We have higher R values, more material needed. So each one is going to consume a little bit more embodied energy. And you can see that building 3 uses a lot more energy than building 2, again, because of that form factor. As we move to material type 2, you can see that our embodied energy went way up. So now we're at 140, where before we were at closer to 40. And this is metric tons of CO2 equivalent. So this is for the entire project. So how much energy went into the materials, specifically the insulation materials within these projects. So using closed cell spray foam and XPS, that has a huge embodied carbon implication. And again, if we're going to passive house, it's going to be more in pretty much every scenario. This changes radically when we look at our low embodied material scenario. This is where we're looking at mineral wool below grade, dense packed cellulose at the walls, wood fiberboard as continuous insulation. You can see that some of our buildings actually have a negative carbon emission. So we've stored more carbon in the material than we have emitted by producing it. And in this case, passive house actually does us a favor because we're actually storing more material. Now, I have kind of a theoretical maybe gripe with this. I don't necessarily want to promote just using more material, but as long as that material is somewhat beneficial, like it's not detrimental, it can actually be a good thing. So not only do we get to better energy performance for operational carbon, but our embodied carbon is way lower. So really thinking about using these materials can do a great deal on our overall carbon emissions portfolio. So here's an example looking at all 4 buildings with all 3 material types at each standard. So you can kind of read the code here. The medium color is the net zero ready. The darker color is passive house. And you can see the total carbon emissions per square foot of TFA. So this is normalized for the size of the building. So you can see the most inefficient building was building 3, followed by building 4. And you can see that the passive house emissions, which is this dark orange, is really high in the material type 2, and significantly less with more conventional materials, and really good when we look at the low embodied carbon material choices. So this is all one side of the coin. Now we need to look at operational emissions of these buildings. So here we have the emissions associated with the energy the building consumes year after year. This is modeled in an energy model process. We're looking at the primary energy for these buildings, and this is measured in metric tons of CO2 equivalent. And you can see that code, does a fairly bad job of preserving energy, right? Even when we go to a voluntary standard like the Department of Energy's Zero Energy Ready Home, we're not getting a huge benefit. We get a huge reduction when the building is built to the passive house standard, right? This can be anywhere from 90 to 75% in terms of the reduction. So we're getting a huge amount of operational emission reduction. And this is really important to think about because the operational emissions happen every year. So this amount of energy use is going to continue to happen year after year. So the operational emissions is something that we definitely want to keep in mind. So let's add together the operational emissions and the embodied emissions for every project. In this example here, I'm using the worst case scenario. So I'm using really high embodied energy materials here, and I'm adding it to the operational carbon. And you can see that the lighter colors, they all reflect the embodied carbon, and the darker colors are the operational carbon emissions. So you can see as a percentage, the embodied carbon takes up a way larger piece of the puzzle. And this is for the first year, right? So we're only looking at 1 year of operation. This does change because we are going to be looking at a building over a lifespan. And if we think about our energy trade-offs, so what are the energy we need to build the building versus the energy that we could save in the building later on, we start to come to a conclusion. So even with the highest embodied carbon materials in scenario 2, it still makes sense to prioritize reducing operational energy use. So projects that are modeled to the Passive House standard offset the added embodied emissions associated with the standard's increased performance in under 5 years. So here we can look at each building and we can look at the additional emissions from the embodied energy. So this is the extra amount of emissions to have X more R value, X better windows. This is the amount of operational emissions we save on going to the standard. So this is year after year. So if we kind of run this out over time, we pay back these emissions in under 5 years for all projects, right? A little bit higher on building 3 and 4, but still within 5 years of the operation. So depending on your building's lifespan, we're hoping that our buildings are going to last more than 5 years. Operational carbons is still a really, really important topic to think about. Here's another way to look at it. If we pick 25 years of operation, that brings us to 2050, which is a big threshold for a lot of our goals. If we just cared about embodied carbon, you can see that the starting point of the amount of energy we need for our code compliant and net zero energy is lower than Passive House. But you can see that the curve is way less steep when we go to Passive House, right? So after 25 years, we're going to be emitting 263 metric tons of CO2, where the other ones were closer to 700, 800. So really the operational carbon is really important. Obviously, if we can do both, if we can think about operational carbon and embodied carbon, we can do really amazing things. So here we're looking at one building, building 2. We're looking at if it was just built to code with conventional materials, what is the amount of emissions for 1 year? If we build that building to Passive House standard with low embodied carbon materials, we can get a huge chunk out of that. So taking a chunk out of both parts of the emission game. So the lesson learned is don't fall into the myth that you shouldn't think about Passive House because it just consumes too much material resource. It's actually really important to think of how the building operates. Not to mention all the added benefits you get from comfort, better health, better acoustics from going to a passive project. The operational energy is still something that's really, really important. And we kind of have this technology. It's not anything groundbreaking. It's using better materials, things like hemp, straw, wood, paper, cork, wool, and incorporating them into our projects. So here's a hempcrete project in Cape Cod, a CLT plus wood fiber project in upstate New York, a bark siding passive house project in Fort Collins, Colorado. So we definitely have this technology, we understand it, and this analysis kind of shows that, you know, embodied carbon is something we definitely want to think about. But in the long run, we still need to consider operational carbon because it's going to just keep adding up over time and over time. So thanks for the presentation. I hope you enjoyed it. I didn't leave a ton of time for questions, but we have about 5 minutes here. I do want to just add that if you want more building science, we have a boot camp in Denver that's starting in September 8th. So you can register that today if you're in the Denver area. There's a lot of incentives. We have some upcoming free presentations as well. There's a open to anyone free info session July 8th. You can come in and ask any questions about Passive House, building science, whatever you want. It's free. We've got strategies for warm, hot, and humid climates the week after, July 15th. We've got Passive House and Indoor Air Quality, August 20th, and High Performance Windows at the end of the month. These are all available on our website. They're free to join, so please look at it. And during our workshop, we'll have a Passive House Builder panel discussion as well. So a lot of things to look out for at emupassive.com. Hopefully we can get some questions in here before we got to wrap up, but thanks everyone for attending.